Okay, so this time we want to explore another method of estimation. It's called Simpson's rule. And what we want to do here is, instead of using rectangles or trapezoids, okay, we want to estimate, okay, grab 2 points, we want to estimate with a parabola instead. Okay, so let's see here. Let's say you have points here, right, evenly spaced out. So x0, x1, x2. What we want to do is use a parabola which will pass through these 3 points, something like this, and use the area under the curve of a parabola to estimate this actual area under the curve. Okay, so it turns out this is going to be more accurate. So why do we want to do this? Well, integral of a parabola, any parabola looks like this, right? ax squared plus bx plus c. This is just anti-power rule, very easy for us to do, right? So that's what we want to explore. Maybe we can do this with parabola, and a mathematician named Simpson did this. That's why hence the name Simpson's rule. So for simplicity's sake, okay, to derive a rule for this, instead of saying x0, x1, x2, let's shift x0 all the way to here. Okay, so let's essentially shift the y-axis here to here. And let's call this 0. Okay, and let's call this minus h and h. Okay, so let's integrate from minus h to h. Now if we do that, right, this is or an opposite interval. This is an even function. This is an odd function. That's an even function. So that will actually just disappear. Okay, so it's the same as this. Because any odd functions, if you do it in an opposite interval like this, the area will add up to nothing. Okay, and also now this is an even function, so we can say let's double it from 0 to h. That's the same as from minus h to h. Okay, let's find the antiderivative of this. Okay, so h0, and we get the expression of ah cubed over 3 plus ch. When you plug in 0, it's all 0. Okay, and this point right here, okay, so here are the parabola points. Okay, so this point, let's say minus h, let's call it y, let's call this y0. This point here, it's 0, let's call it y1. And this point here, h and y2. Okay, and these are all points on the red parabola. So if that's the case, then we can say, well, for this one here, okay, when it's y0, x will be minus h. So you get y0 is equal to ah squared minus bh plus c. And I'm doing this because we want to generate a formula in terms of these intervals x0, x1, x2. So I want to replace the a and c here with y0, x0, y1 and y2. Okay, so that's one condition that we get. Let's now plug in 0 and y1. Okay, for that, we just get y1. If you plug in 0, you get c. So c is equal to y1. And for y2, let's write it here. y2 is equal to ah plus bh plus c. Okay, now how can we express this with y0, y1, and y2? First of all, y0, y1, and y2. And preferably we want to do it in terms of linear combination. Like we don't want to be squaring these. So here, the highest power is degree 2. So let's factor out h. So it's 2h. And maybe let's factor out 3 while we're at it to simplify, get an expression inside without fraction. So we get ah squared. Okay, and here we have to do, you get 3c. Okay, and then if you just add this, and this, you get 3c. And the bh cancels out. So look, ah squared minus bh plus c, bh plus c. Add them all up, you get 2ah squared, 3c. Okay, so it's almost that, but this is not lining up, right? So why don't I just multiply this 2 in to create that? Then you get 6 here, but that's easy to fix. We just need to add more of this. Okay, so there's 3 here. If I do this, I get 6c. Okay, now this here is y0. This is 4y1, and this is y2. So what we have in there, we can replace with y0, y1, 4y1, and y2. Okay, and this is very nice because now, to drive this, we did it from minus h to h. Okay, but now we can shift to the next interval. So the first parabola will be this. Okay, so this is the Simpson's rule, so Sn. Okay, it'll be y0, 4y1, y2. So for the next one, right, we start at x0 to x2. The next one will start at x2. This is where we'll start. So we need, the corresponding, we'll start from y2, and then it'll go to y3 and y4. So that's the next parabola. Okay, so let's see a parabola that looks like that. So this next one here will be h over 3, exact same pattern, but we'll start at y2. So it'll be y2, 4, y3, and then y4. Okay, the one after that will be, we're starting y4, 4y5, and y6. Okay, so if you factor out h over 3, okay, so it's y0 plus 4y1. y2 is now doubled, right? y4 is also doubled. So y3 is 4 times, and y4 is doubled. Okay, and the pattern will continue this way. Okay, all the way to the very last one. We'll just get it once. The one before that we'll get 4 times. Okay. Okay, so notice the coefficient pattern. It's 1, 4, 2, 4, 2, 4, 2, all the way into 4, 1 in the end. Okay, so just to summarize, integration from a to b for a function. To estimate this using Simpson's rule, it's h here is referring to the delta x. So delta x over 3, right? It's going to be f at x0. So this y0, of course, represents f at x0. And then it'll be 4, x at 1, 2, x at 2, 4, right? x at 3, and so on, until it'll be 2f at x n minus 2 plus 4f at n x n minus 1 plus last one will be just f at x n. Okay, so let's use this to approximate the integral from 1 to 2, 1 over x dx. And let's use 10 intervals. Okay, so again, S10 will equal to delta x will be 0.1, right? 1 divided by 10, 0.1 over 3, f at 1, 4, f at 1 plus delta x, so 1.1, 2, f at 1.2. Okay, this pattern continues. Okay, so now when you evaluate that, we'll get approximately 0.693150. Okay, here's the table back from trapezoid, right? So let's just do a comparison. Trapezoid and midpoint. And notice how this is actually much closer to the actual answer already. Okay, I just brought back the true answer here. This was a true answer. Look how close that is compared to these two. Okay. Okay, it's beyond the scope of this course, but so I did S10 here, which was double of what we did earlier with the trapezoid and midpoint. It turns out S2n is actually a weighted average. So you take a third and 2/3, a third of the trapezoid and 2/3 of the midpoint gives you the estimation, the sum estimation of the Simpson's rule. So for example, S10, what we found here, if you take 1/3 of T5 and 2/3 of M5, so 1/3 of this and 2/3 of this will give you this. Okay, try it out. Now this is interesting because this means we actually can get a much accurate result. Okay, more accurate than doing T10 or Mn by doing T5 and M5. Right? This is really useful because S10 is better. It's much better than T10 or M10. But obviously trying to do this with 10 intervals takes a lot longer than doing 5 intervals. This formula gives us a way to get something that's even more accurate than doing T10 or M10 by doing T5 and M5. It's fantastic, right? So it's a much faster way. It's sort of a loophole in a way for us to get to a more accurate result faster without doing the work. Okay, so let's do an example like that as well. Okay, so this is an example of an integral that there's no algebraic method. Okay, there's no antiderivative of this. Because in such cases, we have to use these kind of numerical methods. So let's get a sum that's accurate to 10, cutting up with 10 pieces. But let's use this, which means we can actually get T5, right? T5, and we can get M5. So it's going to be delta x. Right, for this one, it's going to be f at 0. The delta x is 0.2, right? If you cut up into, so it's f at 0.2, but you get 2 of this. 2 f at 0.4, 2 at f at 0.6, 2 at f at 0.8, and then just f at 1. Okay, so this is 0.2. And the trapezoid, the midpoint is going to be 0.2. And we're going to start at 0.1. and we're gonna add, right, 0.2 to that, so 0.3, 0.5, 0.7, 0.9. Okay, so we're just plugging these values into e to the power of, so e to the power of 0 squared, 2 times e to the power of 0.2 squared, and so on. Let's get the values. Okay, so this is what I get. Okay, for these two when I punch it in the calculator, and then now we can get S10 using this. So 1/3 of this, 2/3 of this. Okay, let's punch that in. Okay, I get this, which is, okay, going to be equivalent when you actually find S10 directly. Okay, it's interesting that we can actually use something that's not as accurate to get something even more accurate than doing, trying to make these two more accurate themselves.